All right, guys, this is probably one of the most important lessons for calculus because you have to be really good at solving equations in trig equations in calculus, and I think the majority of them are useful for the no calculator part, so you need to be good. That's part of the reason you need to know the unit circle so well. So trig equations can be very easy or very complicated, okay? I'm actually going to do these out of order. I'm going to go to an easy one here. This is a trig equation. It says find all the values of x for which the cosine is -1. If you just grab your unit circle and you go, well, the cosine is -1 when x is -1, so it happens at pi. And that's the only place on the whole thing. So you say this happens at pi. Now, it does say for all values of x, all. It doesn't give any. So we have to continue on and say, well, we could add 2 pi to that. We could subtract 2 pi from that. And any multiple of that would work. So we're saying pi, add or subtract 2 pi forever, where n is an integer, will give you all the possibilities. So if you were graphing this, you'd have the cosine graph. Okay, and you would say, okay, mine's not very good, it equals -1 at pi, and then 2 pi later, or 2 pi this way. Okay, so all solutions means you have to tell me how often it's going to repeat. But that was a pretty basic equation. All right, they get far more complicated, so I'm going to go back to the top. Now, this very first one that you have is all worked out for you. So just watch me. You don't need to try to take notes on this one. It's all the work is on your paper. There's going to be a lot of this kind where we're going to factor out a function, okay? Somebody's going to want to add cosine over to the other side, and that's not what you want to do. You're going to lose solutions, and I'll talk you through that on a different slide here. But what you need to do is factor out, okay? It's like it says 2n minus n. You would take an n out of both, right? Okay, that's not a good example. If it said here, t times c minus c equals 0, you could take a c out of both and you'd have t minus 1. It's the same thing we're going to do here. We're going to take a cosine x out of both, and you will have tan x minus 1 equals 0. Because remember, the whole idea is that when you are done, this should multiply back to be a tangent times a cosine minus a cosine, okay? So we undistributed this or factored it out. Now, when things equal 0, you have to, say either this equals 0 or this equals 0. So we can say the cosine of x equals 0 or the tangent of x minus 1 equals 0. The cosine is 0. Well, you look at your unit circle and you say the cosine is 0 up here and down at the bottom, so pi over 2 and 3 pi over 2. And the tangent, we can solve this, add 1 over to the other side. The tangent is 1. Tangent always takes a little bit of thinking because it's not on our unit circle, but whenever the x and y are the same, then the tangent is 1. We put the y over the x, or when they're the same here, then when we put the y over the x, you'd get 1. So that happens at pi over 4, okay, up here, And down here in this quadrant, they're both negative. Down at 5 pi over 4 down here. Now, this is a particularly nasty, tricky question because something doesn't check, okay? It's one of the only times you have to worry about this is when you have a tangent in the question. It is the only function that can be undefined on the unit circle. Okay, cotangent as well, but we don't have many of those on these kind of problems. But tangent is undefined if you have 1 over 0 or negative 1 over 0, which happens if you find the tangent, the y over the x here, or down at 3 pi over 2. So it turns out that this doesn't work, which almost never happens, and especially on ones I'm going to assign you. But these don't check because if you try to put them back in at the very beginning, you can't find the tangent at pi over 2 or 3 pi over 2. So the only two solutions that work are here. Now, one way to figure out that there's only two solutions is to graph the original equation, okay, to put this in your calculator and check how many times it hits 0 between 0 and 2 pi. Now, I didn't talk about this, I should have. When you get to the end, now you need to decide, do I put plus or minus 2 pi n on the answer? But this one said I only want numbers that fall between 0 and 2 pi. I don't have to say all solutions. Only want the ones between 0 and 2 pi. So therefore I only need these two solutions, okay? And if I graph this original equation here, tan x times cosine x minus cosine x, and I set, first of all, it got to be in radians, and then I set my window from 0 to 2 pi, this is the graph I get, and it does only have two solutions, okay, where it's crossing 0. But you need them exactly, so you need to do this without graphing. All right. Then, this was the worked out answer, and that was a very tricky one. Okay, just a little more clarification on the plus or minus 2 pi thing. If it asks for all values, and either it doesn't give you an interval at all, or it happens to say negative infinity to infinity, that's when you put on the plus or minus 2 pi n, or your book would say plus 2n pi for whatever reason, I don't know. But for cosine and sine, but if it happens to be a tangent, tangent repeats every pi. So if it said, you know, where is the tangent equal to 1, you could say it's at pi over 4 and straight across, pi later, and every pi after that, okay? Now, this particular question we just did here just said 0 to 2 pi, so you didn't need any of that. All right. This is an extra question you don't have, and I'm not going to spend a lot of time on it, but you do need to know that if you go to solve a question like this, you subtract 1 over here and get 3, you divide by 4, and then you have to square root both sides. Remember when you square root, okay, that you have to do the plus or minus. So sine x equals the square root of sine squared is sine. The square root of 3/4 would be square root of 3 over square root of 4, which would just be 2. But you got to remember the plus or minus. So that one has 4 solutions because the sign could be positive square root of 3 over 2 up here at pi over 3 and 2 pi over 3. Or it could be negative square root of 3 over 2, which happens down here at 4 pi over 3 and 5 pi over 3. So there are 4 solutions to that question. Okay. All right. This one, we are going to isolate the function. It does say all solutions, so we're going to have to do some plus or minus business on the end. Let's see. I'm going to subtract a sine x. You could go either way with this. So I have square root of 3 equals negative 2 sines of x. Everybody get that? Negative sine x minus another sine x is negative 2 sine x. And then I'm going to divide both sides by negative 2. However you want to do it to isolate it, but you get the sine of x is the square root of 3 over 2, and it's negative. So then you go to the unit circle again. I have a copy here somewhere. And you find where the sine, remember the sine is the y value, the sine is negative square root of 3 over 2 at 4 pi over 3, and down here at 5 pi over 3. So this is true when x is 4 pi over 3 or 5 pi over 3. Okay? Now, sine is defined everywhere, so you don't have to worry about extra solutions. I don't know if I graphed this one. Oh, I messed up though. It did say all solutions, not just between 0 and 2 pi. So your final answer needs to say it happens at 4 pi over 3 and at 5 pi over 3, but it would repeat every time you added 2 pi on or subtracted 2 pi, as long as you did it by whole numbers, in other words, a whole multiple of 2 pi, and is any integer. And I'm not going to make you write n is any integer, but that's what it means. All right. So we did this number 1 that was easy. We found the solutions where the cosine is negative 1. Here's just a quick example of why you don't divide by sine. If I had this question right here, I'm telling you need to factor out a sine and then set them each equal to 0, and you'll get a solution where the sine is 0 and the sine is 1. That actually has 3 solutions, I think. The sine is 0, means you went up 0, so that would happen at 0 and pi. And the sine is 1 at pi over 2, so there's 3 solutions. But if you had moved the sine over to the other side and then decided, well, I'm just going to divide a sine out of each of these, you would just end up with the sine x is 1, which would have only one solution. So you would have lost all other solutions, okay? So don't ever, that's what it says over here, okay? Do not divide out a trig factor. All right. So this is that kind of question again, where we don't want to divide anything out. We're actually going to factor out a sine x. That'll leave us sine squared minus 4, which is actually, those are perfect squares. So I suppose we could factor it. Sine x minus 2 and sine x plus 2. I say I suppose because the sine of x equals 0, or the sine of x minus 2 equals 0, or the sine of x plus 2 equals 0. Well, I got news. Does the sine of x ever go up to 2? Does the sine graph? Not unless there's an amplitude stretch, right? It only goes up to 1. There are no sine values of 2, ever. There are also no sine values of negative 2, ever. It's because the sine by definition is a leg divided by a hypotenuse, which can't be greater than 1. All right. The sine of x is 0, though, on the unit circle at the ordered pair 1, 0 and negative 1, 0, which are true when x is 0 and pi. Now this says all solutions, so we need to put the plus or minus 2 pi n on the back. Now, some of you are thinking, well, somebody might be thinking there's a shorter way to write that. Since they're just straight across from each other, you could say 0 plus or minus every pi. It's going to repeat. If you think about the sine graph, it goes through 0, 0, and then it does it pi later, and another pi after that, and another pi this way. Okay, that's a shorter way to write it. Some of you might even be thinking, well, 2 pi works, so you could write 2 pi plus or minus 2 pi n. Okay, those are all true. You could write more of them, just don't write too few of them, okay? So I would have just written these two and called it a day, because 0 is the same place as 2 pi. All right, did we do that on... Yeah, we did on that one. I got nervous. We didn't put all solutions. Okay, so on number 3, we can factor out a cosine on both sides, or cosine out of both of these factors, both of these terms here and here. If we take a cosine out here, we'll have a sine x. Take a cosine out here, we'll have minus 3. This one says all again, so we have to remember our plus or minus 2 pi n business. Take your term being equal to 0, so either the cosine x is equal to 0 or sine x minus 3 equals 0, which means the sine is 3, and that's never true. The cosine is 0 when you have 0, 1, or you have 0, negative 1. Looking at your unit circle, that would happen at pi over 2, and it would happen at 3 pi over 2. Now it does say plus all, so we have to write x equals pi over 2 and every multiple of 2 pi added on, and 3 pi over 2 and every multiple of 2 pi from there on. Now, there is a shorter way to write that, because pi over 2 and 3 pi over 2 are straight across from each other. You could write it as pi over 2 plus or minus pi n, or you could even write it as plus or minus pi over 2, because you could go up pi over 2 or down pi over 2 in the negative direction. And then you could say every 2 pi n or pi n, either one would work. Okay, I'm just going to stick with the basics because I think it gets really confusing when you write things multiple ways, and I don't want to confuse any of you, especially this year when I can't give you lots of feedback on your answers. All right, again, we do not want to divide by a sine of x here because we will lose solutions. So we're going to subtract the sine of x over to this side and make it equal to 0. Then we're going to factor out a sine of x. That'll leave 2 sine squared of x minus 1. Now, 2 doesn't factor other than 2 and 1, and then you'd get a middle term. So we're going to do the take your turn being equal to 0. When things multiply to make 0, one of them has to be 0. So either the sine of x is 0 or 2 sine squared of x minus 1 equals 0. This happens at 1, 0 and negative 1, 0 on the unit circle, which would be 0 and pi. And it does say all solutions, so we can put a plus or minus 2 pi n on the back. Shorter ways to write it, but we're not worrying about it. This one we'd have to solve. So if we added 1 over to the other side and then divided by 2, we'd get a half. Just trying to save a little space here. And then we'd square root. Now, remember when we square root, the trick is you have to remember plus or minus. Okay, square root of 1 is 1, square root of 2 is square root of 2. But when you rationalize that, you get square root of 2 over 2. So it's plus or minus the square root of 2 over 2. So that's all 4 of those ordered pairs on the unit circle that have as a y value square root of 2 over 2 back here, square root of 2 over 2 back here, negative square root of 2 over 2 in the y, and negative square root of 2 over 2 in the y. So there are 4 places that that happens. I don't know if I stuck another unit circle. There, I did. Okay, square root of 2 over 2 here, here, negative 1's down here. It's all the pi over 4's. Whoops, sorry. Was it this one? I just ran. All right. So we had for this question these two solutions, and now this happens at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, some of you realize that there's way shorter ways to write that, okay? If you're at 45 and you need to go to 135, you can add 90, which is a pi over 2. So the shortest way to write that would have been to say pi over 4 and every 90 after that, forever. Add 90 to this quadrant, this quadrant, this quadrant, keep going around. But we aren't going to worry about the shortest way to write it. As long as you get all the solutions, we're good. And I'll be real honest, most of the questions on the test are, the quiz will just ask you to find solutions between 0 and 2 pi. All right, so here's the easier kind I like better. You only have to find the solutions between 0 and 2 pi. My neighbor is using a chainsaw. I apologize. I'm sure you can hear it on the video. Cosine of x is 1/2, easy one here. So where are the two ordered pairs that have a 1/2 at the front? Okay, those would happen up here at pi over 3 and down here at 5 pi over 3. And because it says just between 0 and 2 pi, you don't have to give a list of extra, plus or minus 2 pi n. Nope, just those two are the only two that are going to work. All right, this one looks messy, but what we're going to do is just solve for sine x, isolate the function. So let's see, 5 and minus 7 are on the same side. So that's really just minus 2. So we have 2 sine x equals 2, sine x equals 1, and the sine is 1 at this ordered pair only, which happens up at pi over 2, and that's the only place. Liking those a little bit better? Okay, I hope you did, but now they get tricky. Actually, this one's not too bad. We're going to subtract the tan x over so that we do have it equal to 0. And then we are going to factor out a tangent of x. Now, this time 4 is a perfect square, so we could factor this further as 2 sine x minus 1 and 2 sine x plus 1. It's kind of like we have a 4x squared minus 1, right? It would factor 2x plus 1, 2x minus 1. All right. And then we have the tangent of x here. So one of those three things that's multiplying has to be 0. So the tangent of x could be 0, or I'm going to solve this one. The sine of x could be 1/2, or if you set that one equal to 0, you'd have the sine of x equals negative 1/2. I didn't show all the steps, but I hope you can follow those. Now, we have to be a little bit careful whenever we see tangent of x, because remember, the tangent of x is undefined 2 places. It's undefined at pi over 2 and 3 pi over 2, so we have to be real careful that we don't put those down as answers when we see tangent. Do I have a unit circle close by here? Here we go. We need where the tangent is 0, so putting y over x, 0 over 1, and 0 over negative 1, so 0 and pi. And because it's tangent, it doesn't matter. I'm going to say we could put 0 plus pi n, but we only want the solutions on the unit circle. So one happened at 0 and one happened at pi. Now the only reason I'm not writing, oops, I don't know what just happened. The only reason I'm not saying that we need to include 2 pi is because if you look back up here, this parenthesis said don't include 2 pi. Okay, it did not have a bracket, it had a parenthesis. Up to but not including 2 pi. If it had a square bracket, then you'd want to include 2 pi. I'm not going to be tricky on that. Okay. Where is the sign 1/2? Means I'm looking for ordered pairs that have a 1/2 at the back. And that would happen at pi over 6 and 5 pi over 6. And a negative 1/2 would happen at 7 pi over 6 and 11 pi over 6. Now, tangent is undefined at pi over 2 and 3 pi over 2, and we didn't get that on our list. So we are looking at there being 6 answers to this. I don't think this is one that I graphed to check. Let me see. Nope, I did graph some of them, and I'll show you some of those. I guess I could graph that one quick now if you wanted to see. It said 4 sine squared times tangent equals tangent. So you would very carefully make sure you're in radians, and then you would type 4. Now there's 2 ways to do this. I was always taught to put the sine of x in the whole thing in parentheses and then square it. That's the way that used to work. Now you can actually do it a little shorter, and I'll show you on another one. Tangent of x, and that's supposed to equal tangent of x. So between 0 and 2 pi, if I have my window set from 0 to 2 pi, and I graph this, there's 1, 2, 3, 4, 5, 6, and almost 7 places that it crosses. That's because the 7th one is right at 2 pi. Okay. All right. So this is an easy one. First of all, it's easy because it only has one function. We just need to isolate it, add square root of 3 over there, and then divide by 2. And it's easy because they only want the solutions that are between 0 and 2 pi. So we look on the unit circle for where this is true. And that happens at, let's see, pi over 6 and 11 pi over 6, I think. Let me find you a unit circle to double check. Here we go. All right, cosine pi over 6, 11 pi over 6. And that's it. All right, then there are some tricky ones, and we will do more of these in a couple days, but there are some tricky ones where you have to make a trig trade first. And I want to show you just a couple examples today. This is a tricky one. When you have a tangent squared and a secant squared, you already have this one worked out, so just watch me. But these are squared functions, so there's a trig identity. There's a trig identity that says tangent squared. Whoops, I didn't write that right, but I'm in a hurry, so I'm just going to leave it. Plus 1 equals secant squared. So that means a tangent squared minus a secant squared. Oh, this is a 2 tangent squared. Okay. I was like, what's going on here? Why can't we just trade this? But we can't. All right, so what we can trade the secant squared for is a tangent squared plus 1. And the reason we want to do that, plus 3 equals 1 minus 2 tangent of x, because we can manipulate the squareds, but we can't ever trade anything for a tan x. So we have to make this all in terms of tangent. So I'm going to do some algebra real quick. Distribute that negative. Then I'm going to combine these and get a tangent squared. Let's see, I have a -1 and a +3. That would be a +2. And I'm going to subtract this 1 over to that side, so I wind up with a +1. And I'm going to add this 2 tangent over here. And then it's going to factor tangent of x plus 1 times tangent of x plus 1. Because, remember, it was a tangent squared plus 2 tangent plus 1. Does everybody see how that will factor? Okay. So then we have set each of those equal to 0, and we get the tangent of x equals -1. Now, tangent is tricky because it's not on our unit circle. But the tangent of x would be 1 if we had a square root of 2 over 2 here and a negative square root of 2 over 2 here, or a positive here and a negative back here and a positive up here. So the two places that happens, where they have opposite signs but the same x and y values, are in quadrant 2 at 3 pi over 4 and in quadrant 4 at 7 pi over 4. Now, I graphed this one, okay, to show you that there are indeed one solution here and one solution over here. And here it is with their book's work. Okay. Now, this is a uber tricky one. What you have to do here, and I'm not going to ask you one like this on a test or quiz most likely, but you have to square both sides. So you would have 1 plus cosine of x times 1 plus cosine of x equals sine squared of x. And then the sine squared you can trade out for a 1 minus cosine squared. That's an identity, right? Sine squared plus cosine squared equals 1, and we want all the same function here, so we don't want to get rid of that sine squared since we got cosines over here. So if we rearrange this, a sine squared is a 1 minus cosine squared, and I'm going to put that in there. So over here I'm going to FOIL this out. And here I traded that out. All right, I'm going to add the cosine squared over here, so I end up with 2 cosine squareds. I added this one. Okay, then I'm going to subtract 1 from both sides. That'll get rid of that. And I'm going to add these two together, so I have 2 cosine of x, and I have equals 0. So then I can take both a 2 and a cosine of x out. That'll leave a cosine of x plus 1. So the solutions I'm looking for, now if 2 cosine of x equals 0, I can divide by 2. I still have the cosine of x as 0. And here I have the cosine of x as -1. So that is true. Cosine is 0 at 0, 1, at 0, -1, and the cosine is -1 at -1, 0. So those places are at pi over 2, 3 pi over 2, and pi. Let's see if I graphed this one. Actually, I graphed this one by hand. It said, where is 1 plus cosine, which would just be a cosine graph shifted up, equal to the sine, and the red I did the sine of x, and there's 2 solutions. Did I have 3? What did I do wrong, guys? The cosine is 0. Three pi over 2 doesn't work. Okay. So 3 pi over 2 doesn't work because when you put it back in, if you put 3 pi over 2 in right here, 1 plus, okay, the ordered pair at 3 pi over 2 is 0, negative 1. So if you go back to the original equation, 1 plus the cosine would be 0 equals the sine, but the sign down there is negative 1. So that's an extraneous solution that we got because we squared it. So then the negative 1 became positive 1. Whew. Yep. I don't think I'll be asking you that on a quiz. Especially not yet. Okay. I don't think I ask any where you have to square both sides. This one is square rooting. We're almost done. You would square root both sides. So you'd have the tangent of x equals plus or minus 1. And that happens all of those places where you have square root of 2 over 2's. It's either positive or negative 1 for the tangent. This wants all solutions. So you could list pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Now, this is a tangent. So the tangent has a period of pi. So you really could just list a couple of them and then say, and straight across at pi units later. Okay? So you could say plus or minus pi n and plus or minus pi n and be done by just listing a couple, or you could list all of them. I'm not going to be picky. All right. This is a tricky one because you have to trade out a trig trade here. You can't get rid of cosine, but you can trade this for a 1 minus, so sine squared plus cosine squared equals 1. So sine squared would be a 1 minus cosine squared. So I have 2 times 1 minus cosine squared minus a cosine, and I'm going to subtract that 1 over and make it equal to 0 while I'm here. All right, distributing gives me 2 minus 2 cosine squareds minus a cosine minus 1 equals 0. This 2 minus the 1 back here is a 1. Now I have this, but I'm going to trade all the signs, change all the signs, because I don't like factoring when there's a negative a. All right, so then I have 2 cosine of x. Remember, this is like a 2c squared plus c minus 1. That would factor 2c times c, a 1 and a 1. Let's see, to get a negative, positive in the middle, you need a plus here and a minus here. Let's see, 2c minus 1c is 1c in the middle. Oop, I lost an x. So then we wind up with the cosine of x is 1/2, which happens when x is 1/2, which would be at pi over 3. And do I have a handy unit circle somewhere here? Should be 5 pi over 3. X is 1/2 up here at pi over 3, and down here at 5 pi over 3. Ugh, is this the one I was working on? And here the cosine of x is -1 when you have -1, 0, which is at pi. Now, I think I graphed this one because we did a lot of crazy manipulations here. So I graphed the original function, and here's where I showed you that you really can just put the squared here, and this is the same as 2 sine of x squared. They reprogrammed it so you don't have to do the double parentheses anymore. So this is what you get when you graph this, and our equation was, does it equal 0? And we got 3 solutions here, and that's what we came up with, right? Was 3 solutions? Pi over 3, 5 pi over 3, and pi. All right. 2 more. This is easier than it looks. You could do some crazy business, guys, but you know where the cosine and sine are equal on the unit circle. The only time that happens is when you have a square root of 2 over 2 or a negative square root of 2 over 2. So the only place that happens is at pi over 4, and let's see, that would be 5 pi over 4. Okay. If you thought about the cosine graph from 0 to 2 pi, and you thought about the sine graph from 0 to 2 pi, okay, it happens twice. That's it. And last but not least, just one more quick review where you take out a cosine of x. But this is an icky one again because it has a tangent. So the cosine is 0, or square root of 3 tan x equals 1, or tan x equals 1 over square root of 3, which rationalizes, but it doesn't really matter. We're using this. We need to find this ordered pair, okay, either both positive or both negative, to have this be the tangent, because it's y over x. So that ordered pair happens at pi over 6, and if they happen to both be negative, then it would happen at 7 pi over 6. Now the cosine is 0, happens when x is pi over 2 or 3 pi over 2. And I wouldn't have caught this probably, but I think I graphed it and realized it was true. But is the tangent defined at those places? If you went to plug that back in, the tangent is undefined at these 2 places, so we can't include those. And again, I think what I did was I graphed it and realized it only had 2 solutions. Okay, and they were at pi over 6 and 7 pi over 6. All right, that's the last one. Sorry this video is eternal. We'll do more equation solving yet on Friday. Aren't you excited?